So on a test or quiz, just be careful about whether it's an ideal spring or not. Let's actually test it one more time. Let me add 100 onto the end. And again, trusting them for some reason. So if I put 100 grams on here, what would you expect the period to be? Even? Yeah. Wow. I suspect it's gonna be about 1.7 something.
I got 1.82 or 1.830 basically.
830?
Yeah.
All right. Let's find out how well we do that. Yeah, last time, if we had gone more than 10, at some point it seemed like it was getting a little bit closer and closer to the table. All right, so ready for timing? This time I'm going to lift it up. All right, 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do we got?
17.69.
17 point,
69.
okay?
17.79. 17.44.
17.32.
17.64.
And we're expecting 18.3, so we're looking at an average of about 17.6. Not as good as I was hoping, but hopefully close enough. I believe we're about to get the actual average.
17.558.
So 1.756 second period, and we predicted 1.830. About 7% error. All right, let's take it to the next step. If I took that we'll take the one I just did, and I wanted the equation. So delta y is equal to a cosine omega t plus phi. This is the generic, you could use sine also, but this is the generic equation for something in simple harmonic motion. This phi here is known as the phase shift. And that's to account for the fact that we're not always starting this at 0. That it's quite possible for me to just get it going, and then we start timing it at some point after it's already started moving. But if we're at our maximum value at time is equal to 0, the phase shift is 0. So phi is equal to 0. if uh, if at t equals 0 seconds, delta y is equal to the maximum value, the amplitude. So if I took this spring and I pushed it up, say 15 centimeters and let go, well, the equation, my displacement, is going to be equal to 0.15 meters times the cosine of omega t. Well, we have a formula for omega, we can pull it from that, but omega is the square root of k over m, which is the square root of 1.738 divided by 0.0474 plus 0.1. And so what is the angular frequency? Units?
Radians per second.
Yes. So our equation becomes our amplitude, how far I pushed it off of equilibrium, times the cosine of 6.06 radians per second times time plus 0, since I started it at the maximum value. Anyway, so we have an equation. So at this point, we can now make predictions about at some time where the object is. Yes?
Did the 0.15 come from how far you stretched it when you started?
Yes. Or in that particular case, how far I pushed it up. Other questions?
I got something different with the angular frequency.
Pardon?
I got 3.434.
You got 3.434? All right, so there's that plus 0.1 there. So 0.14, so that's gonna be 10 point something, so that 3 point something makes more sense. What'd you get again?
3.434.
All right, assuming that we've done it perfectly and 1.830 seconds is the amount of time it takes to go all the way down and back, at what time will the displacement, let's give ourselves some room here. At what time is delta y equal to negative 0.15 meters? There are two ways of solving it. So I'll move into either one.
It's at a quarter of the period way through.
A quarter of a period? Why a quarter?
Because you're going from the half.
Yeah, It is, so the quickest way of doing it is recognizing that's half a period. That's how long it takes to go from here to here, and it's and it's turning around. So it should be 0.915 seconds. How else could you have done it?
Could you set the equation equal to negative 0.15 divided by 0.15, take the arc cosine of -1, set it equal to your number times g?
Absolutely. So the other way, negative 0.15 is equal to 0.15 cosine of 3.434t. Divide, get rid of this, so we have -1 is equal to the cosine of 3.434t. Arc cosine. Now, this is one of those places where we're suddenly switching. We've been using degrees up until now. We're now dealing with radians. So when you do the arc cosine, you should get pi is equal to 3.434t. And pi divided by 3.434 feels like it's somewhere around 0.915. If it's not, then it's either rounding or we made some other critical error. It is. Okay. At what time is this within the first period? Is it going to maximum speed?
Would that be a quarter of the period?
Yes, it would. So it starts out at some amplitude. It's going to get faster as it drops, but once it gets past equilibrium, it's going to start to slow down.
So if we're talking about an imperfect spring or an unideal spring, would the fastest moment always be the first quarter of the first period?
Ideally, for a non-ideal spring, yeah. It would be, well, actually, a quarter and 3/4.
Well, 3/4 is it gonna come back with the exact same speed if it's
No.
not ideal?
For what we're doing, yes, but you're right, there is some dampening going on. Does slow down as it goes, but yes. I would assume that I would go for a quarter and 3/4 of the period. What's the formula for the velocity of this?
Change in position over change in time.
Okay, that might get a little bit tricky. Because it's not a straight line, finding the slope is not particularly easy. So we have delta y is equal to amplitude cosine of omega t plus 5 generically. What does the slope of a cosine curve look like? We did this
Sine
last
curve.
Thursday. Pardon?
A negative sine curve.
Yeah. So negative a times omega sine omega t plus 5. So my velocity in this particular case will be negative 0.15 meters times omega, which we found was 3.434 radians per second, times the sine of 3.434 radians per second, times time. And so what is this?
Your amplitude.
Okay. More specifically, what's the number?
Negative
5151 units? It sounded like you stopped midway.
Is it radian meters per second?
Yeah, if you wrote down radian meters per second, I would accept it. However, remember radians is a unitless unit. So when it's convenient, just don't write it. It's also, we're looking at velocity here, so it's meters per second, times the sine of 3.434 radians per second times sine. So our maximum velocity, or sorry, maximum speed is 0.5151 meters per second. So V max. There's no vector symbol over that, V max, 0.5151 meters per second. But I have this thing oscillating up and down, and the forces acting on it are the spring force and the gravitational force. What is special about gravitational force and spring force?
They're conservative.
Yes. So we should be able to also solve this with energy conservation. So I started out at, this is equilibrium, and I started here, some initial amplitude. At this point right here, it's all potential, because it's not moving yet. So I have 1/2, well, energy is conserved, energy initial equals energy final. So K initial plus U initial equals K final plus U final. You all know it. What's the formula for kinetic energy?
1/2 mv squared.
Yeah. Plus. Now, this is an interesting thing about this is we've got these two conservative forces acting on it. But remember that without anything on it, the spring is up here. Putting the mass on it, it now sinks down to here to be in equilibrium. So is my displacement here based upon the equilibrium with nothing on it, or the equilibrium with the mass on it? If you choose equilibrium to be the point where the mass is, with the mass on it, we don't actually bring in gravitational potential energy. So it's just going to be 1/2 K delta X squared. Initial. If you take it from the original position, you do have to bring gravitational potential energy into it, and you're just making more work for yourself. And 1/2 mv final squared plus delta X final squared. All right, what can we get rid of? Coin?
Is there no potential energy at the bottom because it can't go any further?
The potential energy is taken into account that this keeps increasing the farther it gets away from equilibrium.
Okay.
You talking about MGH?
I'm talking about the first half, the second half of the first half of the equation. The 1/2 K delta X squared. You said we don't have to do.
We don't have to do MGH if we're looking at it if delta X is from the equilibrium position with the mass on it.
Is that because it's at the lowest point that it can be? Or because it's not moving up and down?
It's not, because it's not accelerating at that point. And there's a video I go through where I actually show that the MGH cancels out. So what can we get rid of?
1/2.
All right. Anything else?
Delta X initial.
Ooh. Delta X initial, that's the point where I release it.
Initial velocity.
Yeah. So I'm left with K times my amplitude squared. See how well this works. Is equal to mv final squared plus, if we're trying to find the maximum speed, where does maximum speed occur?
Fourth of the period.
And what's the location of the fourth of the period?
The minimum or maximum?
Is it half the amplitude?
Not half the amplitude. Minimum and maximum presumably would, in our case, would be 0.15 and negative 0.15. Definitely, those are the turnaround points or the starting point, so that definitely is, that's where the speed is 0.
So is it at zero displacement?
Yes. A quarter of the period is, it starts here, that's half, that's a full period. A quarter of the period, that's the equilibrium point. So that would be 0 as well. So what we're left with is VF becomes A, the amplitude times the square root of M over K. Try that one again. K over M. That is just the angular frequency. So our maximum speed is at the amplitude times the angular frequency, which is what we have right there. We have two different ways of solving the exact same problem. And likewise, to find maximum acceleration, we have two ways of doing that as well.
I have a question.
Yes?
Why is where did you get the maximum speed is 0.5151 from that previous equation?
It's the amplitude of this equation.
And why is it the maximum speed?
If I've got this function right here, at most could be 1 and at least could be negative 1. So the most, I'll be multiplying by this as 1 or negative 1. Those are my extremes.
Okay.
So therefore, that's the maximum. That does not a look of someone who's convinced of it.
No. Well, so if the max, but are we multiplying by half the max? Or a fourth of the max, or no?
No, that, if we wanted to find it by plugging in time is equal to a quarter of the period, that this whole thing should be equal to either, the whole thing would be equal to 1. And so we get